Let's go over the entire Calculus 1, the study of change and motion. Functions. This is mainly learned in algebra, but it is ultimately the foundation of calculus. Functions relate a set of inputs to a set of outputs. A function that exists in 2D takes in an input in the x-axis and outputs a value in the y-axis. Doing this for many values gives you a graph. A function must specifically have either the one-to-one relationship or many-to-one relationship to be considered a function. You can use the vertical line test to see if a function is indeed a function. Simply make a vertical line through your graph, and if it intersects more than one point, it is not a function. Limits. Limits describe how a function behaves near a point, not on the point itself. There's a value that the x always approaches and gets infinitely close to, but never touches. The general expression of limits is this. It is read as the limit of f of x as x approaches a is the value L. These limits are evaluated usually by substitution or simplification then substitution if the limit is initially indeterminate. Continuity. Sometimes, if these limits diverge or don't exist, discontinuities are made in our graph. There are three types of these discontinuities. The whole discontinuity, which looks like you have a continuous graph except for in one little point or hole. The jump discontinuity, which is continuous until a certain point, where the function jumps to another value and continues from there. Then you have the infinite discontinuity, where asymptotes force the function to diverge. Functions are considered continuous at a point as long as they are defined at the point, the limit exists at the point, and the value of the function is the same as the value of the limit at the point. Derivatives. Derivatives are what we use in calculus to observe the rate of change of functions. This is especially useful since it allows us to analyze the instantaneous slope of functions at certain points, as opposed to what we used to do before calculus, which was simply taking average slope. Derivatives are usually denoted using the Lagrange and Leibniz notation like this. You can even take higher order derivatives, which is just taking the derivative of the derivative to get the slope of the slope. Differentiation rules. These are the rules we use to actually evaluate and take derivatives. These are the constant rule, constant multiple rule, sum rule, difference rule, product rule, quotient rule, and chain rule. Applications of derivatives. We can only imagine how powerful derivatives actually are. They're used in many practical ways, from knowing the instantaneous velocity of an object given a displacement function, to optimization, where you get the maximum or minimum value of a certain quantity. Integration. Integration is used to find areas and volumes under curves by summing up infinitely small slices under the function. Here, we see that you can slice up the area under this curve into 6 rectangles. This gives you a rough but inaccurate area. You can increase the slices to 12, which becomes slightly more accurate yet still not 100% correct. Finally, you can increase the slices to an infinite number to get the exact area under the curve, which is exactly what the essence of integration is. Types of integrals. There are two overarching types of integrals. The first, the indefinite integral, outputs the antiderivative of a function. This means that taking the antiderivative of a derivative function gives back the original function. The second is the definite integral, which outputs a number. It is the area under the curve f of x from x equals a to x equals b. And that's it. Some details were left out, but that's essentially the gist of Calculus 1, the start of your journey into the beautiful world of calculus.